Hi everyone. This is one of my favorite slides in all of 203, and it's really expressing the combination of electricity, relativity, and magnetism. Now if you remember when we talked about or introduced magnetism, we introduced this basic fundamental fact that parallel lines of current attract one another, oppositely oriented parallel lines of current repel one another. And we use that fundamental formula to derive the Lorentz law, and ultimately that drove us to talk about how Faraday's law is the consequence, and Faraday's law drove us to talk about Maxwell's equations. Maxwell's equations drives us to talk about relativity. So really, all of this is a consequence of that fundamental fact which I introduced arbitrarily. I said this is a fact of nature. Here we're coming full circle, and I want to justify that from a theoretical standpoint using Coulomb's law and relativity. So we do that by just setting up the situation. That's what's going on the right side here. I've got a line of current which is generating a magnetic field. That magnetic field curls around. On the right side I've got a magnetic field coming out. On the left side I've got a magnetic field going in. Imagine there's a test charge, a positive test charge here, and because there's a magnetic field, it won't experience any force unless it's moving. So imagine it's moving down the page. So I've got a magnetic field that's pointing into the paper at this point. If I use the right-hand rule, I've got to align my thumb with the speed, the velocity vector. That's going to generate a force out, a magnetic force away from the current. Now that makes sense, right? I've got current going up. This effectively is current going down. I expect a repulsion due to the magnetic force. Now, before I move over here, just remember that this conventional current is moving in the opposite direction as the actual electrons. The physical electrons are flowing down the page, okay? But there is no net charge here. There's a one-to-one relationship between the pluses and minuses. You know, we've talked about that before. Now's where we mix in the relativity. Imagine I have the same setup, but in this case, I'm moving the whole setup. It's in motion. And we know that from one of the results of relativity is that systems in motion, my perception of what's going on in those systems, in those moving systems, is different than the perception inside. So on the left, we've got the perception inside. This is the perception outside, and I want to talk about this. So we imagine that this laboratory, not moving up, was moving down the page, okay? I want it to move down the page, and not only is it moving down the page, it's moving down the page in such a way that it matches this speed. So in this frame that's moving, it's moving with the charge. So basically, essentially, the charge is just sitting there, right? And everything's moving. Let's see if the charge is down. So, everything is moving up the page, right? So if I want the charge to just be sitting here, I've got to have everything in the lab moving up to compensate. So I imagine everything's moving up the page, which means not only do I have current, but I have a little bit more current flowing. This current, remember, current is just the amount of charge that flows per second. I have more charge flowing now because it's moving faster. So the current's a little bit larger. I have a little bit larger magnetic field. But it doesn't matter because this charge isn't moving at all. From my perspective, it's not moving. It's not going to experience any magnetic force at all, no matter how large. However, if I look at what's happening in the wire here, kind of expand this out again, the positive charges in the wire are actually moving up. Okay? Because remember, everything's moving up. Here, the positive charges were stationary, the electrons were flowing, that's where the current was, but the positive charges representing kind of the substrate of the wire are stationary, but here they're flowing up. Because they're moving up, length contraction comes into play, and this is where relativity mixes in. Length contraction, the spacing between these positive charges decreases. So So now instead of having 4, I've got 5 in a certain, maybe per centimeter or something like that, right? So that happens to the positive. What about the negative? The negative charges are flowing down here, but here, since everything's moving up, the charges aren't flowing as fast as they were before, right? And so, because the speed decreases for the electrons, they suffer the inverse of contraction, right? There's an expansion between them. So we get length contraction because we go from 0 to something for the positive charges. We get an expansion because we go from something to something smaller for the electrons. In the end, in this little space for this example, we've got 5 positive charges, we've got 3 negative charges. We've got 2 extra positive charges than we ought to have. In other words, the wire is positively charged on a net basis, right? This is a positive charge also. Coulomb's law tells me that positive charges repel one another. And so I get a net force to the right, and if you figure out all the mathematics, these forces are exactly the same direction, the same size, but my interpretation of what they are is different. In the one case, I've got a magnetic force, and in the other case, I've got an electric force. And so this shows in a very neat and compact way how the electric force, combined with some relativistic arguments, can explain where the magnetic force is coming from, and really brings together and unifies the entire subject.